Ben Gertzel here, coming at you from Frankfurt Airport. I'm halfway home from Addis Ababa to Seattle. It's been an intensive few days in Addis at our AGI workshop. Super successful, very exciting. I was hoping to capture some video there, but it was just too intensive with all the meetings and stuff. You know, there were two big objectives we have with the Meetup. One is every 6 months or so we do a face-to-face gathering of a whole bunch of our AGI R&D team. The other was I wanted to connect our amazing Ethiopian developer team better with our global AGI R&D and platform development team, because I'm back and forth to Addis all the time. It's like a home away from home, but most of our global team knows the Ethiopia team only through the internet, and building those face-to-face connections is important even if most of your work is online. So we got both those things accomplished pretty interestingly. I would say, in the last Hyperon meetup we did 6 months ago, the theme was like, wow, some of the tooling is finally working. We had the PETA interpreter for the meta language, we had Mork, this in-RAM knowledge graph, and they were working pretty nicely 6 months ago for the first time. So I was like, well, now comes the time when we set about scaling up all our AGI algorithms, right? So now, this meetup, indeed, we're in the middle of scaling up our AGI algorithms, right? And it's a bit of a story, but it's a story that overall is coming out pretty well without any super nasty plot wrinkles. So, like, just to give a flavor of the kind of thing we're doing, one of the core cognitive algorithms in the Hyperon design is PLN, probabilistic logic networks, which is a kind of reasoning that it's good at combining linguistic, qualitative information, visual information with, relational database, quantitative information, put it all into this logic engine, draw logical conclusions. And compared to an LLM, it can do reasoning in a way that's really grounded in observed knowledge rather than just kind of throwing words together willy-nilly, right? So there's two primary ways of guiding this kind of inference network. One is called forward chaining, where you have one idea, then that follows to another idea, that leads to another idea, that leads to another idea. The other is called backward chaining, where you start with some conclusion you want to get, and you see, well, how could I get that conclusion? How could I get to that? How could I get to that? How could I get to that? And kind of go back from where you want the inference to go to. So one of the challenges we have now is make both forward chaining reasoning from what you know onward and backward chaining reasoning from what you want to learn backward, how to make both of those work at scale, right? So we had a presentation from Neil Geisweiler, who I've been working with on probabilistic inference since 2008 or something. What Neil found was that forward chaining inference worked very fast in Mork, our in-RAM knowledge graph. Backward chaining inference, as he implemented it, was not that fast in Mork, but was very fast in PETA, our prologue-based meta-interpreter. And we're looking at why. As we look at it, we realize if you implemented backward chaining a bit differently, more after the pattern of forward chaining, you can make that fast in Mork as well, right? So we're dealing with a whole bunch of issues like that. Go through each AI algorithm, look at the different cases of it, figure how to make the different cases go fast on large amounts of knowledge in the various tools that we have now for the infrastructure of Hyperon, right? So it's a bunch of detailed work, but we're crunching through it. And I mean, so far what we see is if you're careful and smart and do things right, I mean, we can get probabilistic logic reasoning, we can get concept blending, we can get program learning, like we can get our key cognitive algorithms in our Hyperon AGI design to work at scale on these infrastructure tools that we've just gotten working over the last half year finally. So it's been quite exciting and interesting. And I think one of the challenges we're confronting also is the whole field is advancing so fast with so many cool things happening from other people as well. I mean, we have to balance proceeding resolutely with our own AGI design, our plan for building a thinking machine, which I wrote out in the book Engineering General Intelligence in 2014, based on thinking largely done before that. Implementing that step by step in a systematic way with making use of the cool new things that are coming out in the AI field at large, right? And there's a lot of interesting balancing acts to do there. So for one thing, like we can use LLMs together with Hyperon and together with our own tools, right? Even if you don't fully trust an LLM's reasoning, it's very impressive, right? It's cool, and you can use PLN, logical reasoning, which is better grounded in real-world information and doesn't hallucinate so much. But you can have that talk to LLMs and use LLMs to help guide PLN's reasoning, and use PLN to help put new stuff in an LLM's prompts. And this back and forth between LLMs and PLN, like this was not part of our original AGI design from my 2014 book, Engineering General Intelligence, but LLMs are there. Like, why not use them if you can plug them in without compromising the integrity of the AGI design? You know, let's keep PLN, which is core to the AGI design, but let's allow PLN to get juiced up by LLMs. Like, why not? And then let PLN help juice up the LLMs. You have a mutual feedback. On the other hand, while using LLMs as they exist now makes loads of sense, they're incredibly powerful, they're still not AGI worthy, right? Like they don't do continual learning among other things. Like you can train them to a certain level, then you have to freeze them and don't let them learn anymore, or they'll start to forget stuff and get confused. And that's why you have discrete models like GPT 5.4 or Cloud Opus 4.6, because these LLMs cannot continually learn. They can learn up to a certain point. Then before they start to catastrophically forget, you have to freeze them and just use them for inference. Don't let them learn anymore. So while we want to use the LLMs that exist now for what they can do to enhance our Hyperon AGI methods, I mean, we also want to make LLM-like neural nets that can do continual learning, right? I mean, because then you can have, a bunch of LLMs talk to each other and constantly learn from what they're saying, revising their link structure. You can have the LLM revise its link structure dynamically based on its interactions with PLN, right? I think we know how to do that using a collection of learning methods called predictive coding and a variation of predictive coding I made up called causal coding, right? And that makes a lot of sense mathematically. We have some small-scale examples showing that predictive coding can do continual learning better than the standard backpropagation method used to train neural networks, but there's a bunch of work needed to scale that up also, right? And we had a team in Addis working on scaling up predictive coding for training transformers. We've made a new software framework for predictive coding, Fabric PC, brewed up by Matthew Barron, another of our developers based out in Seattle near me. And Fabric PC, it's the first production-grade software framework for training neural nets with predictive coding rather than backprop. And Matthew came out of Microsoft, out of the Bing team. He had a lot of experience with production-quality software. We had an amazing hackathon in Addis Ababa with a whole bunch of our developers there. Spend a few hours hacking with Matthew's Fabric PC framework, and they could blow up, a fluid dynamic neural network, a Bayesian-based transformer, right? It's amazing how quickly the developers could whip up different neural architectures and train them using Matthew's Fabric PC framework. And the goal there is to, once we scale these things up more, you can replace the current transformer neural nets that can't continually learn with transformers trained by predictive coding that can continually learn more like neural nets in the brain. And that doesn't replace Hyperon. It's more like creating neural half of the neural symbolic hybrid system that works better, because you really want Hyperon with its symbolic and evolutionary AI to work together with neural net AI, but in a way that has very rapid feedback between the two pieces, right? And another example of tap dancing a bit to adapt our long-standing AGI designs to cool new things popping out is MetaClaw, right? Like I saw OpenClaw, I'm like, we can do that better in Meta than in TypeScript. So indeed, Patrick Hammer and our developer team wrote a couple hundred lines of Meta, wrapping up maybe 20 lines of TypeScript, and you have MetaClaw, which is much more compact and elegant than OpenClaw, and you can more easily add various kinds of long-term and working memory and reasoning into MetaClaw than into OpenClaw because of its foundation in Meta, which is an AGI programming language. So now we start thinking, okay, you have all these different cognitive processes in Hyperon. We used to have something called the COG server, which allowed all the different processes in Hyperon to be scheduled in a cooperative and adaptive way. Well, why don't we just make MetaClaw the COG server, right? You can just use MetaClaw as the software process that orchestrates all the different cognitive processes in a Hyperon instance. And that can do everything our old COG server, cognitive process scheduler, was doing, and it can schedule in all sorts of other processes reaching out onto the internet, right? So then you get a cognitive process scheduler inside Hyperon, which is also reaching out its tentacles all over the internet, right? And that's not what we said in 2014 in Engineering General Intelligence book. On the other hand, it's better. It does all that, and then it's agentic in the modern sense as well, right? So we had a lot of interesting discussions like that in our meetup in Addis, where it's like we need to stick with our core AGI design, which is based on a bunch of math and a bunch of deep systems thinking about how all the different parts of a human-like mind with beneficial motivation and the ability to uplift to superintelligence, what this architecture needs to be. But within the scope of this overall architecture, which is fortunately fairly flexible, we want to weave in the best of what the world has to offer in modern AI, which is evolving so fast, and then upgrade the best of what the world has to offer, right? Use transformers, upgrade them to PC rather than just backprop. Use a claw, but don't just plug in OpenClaw. Upgrade to MetaClaw for better cognitive process integration. Anyway, a lot more interesting stuff than that going on. Maybe I'll give you a small flavor of a few of the things we've been discussing these last few days. Now I'm heading back home to Seattle, see my wife and kids again, and sit down at the desk and maybe get some coding done on predictive coding for continual learning. Actually, after some of the discussions in Addis, I had some ideas for putting causal coding together with a cortical column-based neural architecture, and given codecs, it's possible to turn a concept like this fairly rapidly into a prototype to play with, right? And I'm not doing any large-scale coding now because my time is needed sort of coordinating everything, keeping everything toward the big picture. But given how easy it is to whip up prototypes using modern LLM coding tools, I can spend like a day and whip up a prototype of a new neural architecture for causal coding learning, and if it's reasonably promising, I can turn it over to someone else on the team to try to really test it and scale it up. In the meantime, once again, I'm recording a video right before boarding a flight. Time to hop on the plane back to Seattle, where I will be home for a few weeks, getting some actual work done before setting out anywhere else. So, until the next time.